Welcome back everyone. In this video, we are going to learn 8085 microprocessor logical instruction in the simplest way possible. We will understand comparison instruction, logical operation, rotate instruction and flag manipulation with easy explanation, visual representation and solved example. So if you are preparing your semester exam or learning 8085 from scratch, this video is for you. Let's get started. In our previous videos, we have learned about data transfer instruction and arithmetic instruction. Today we are moving to another very important category of instruction, logical instruction. This instruction play a major role in decision making, data manipulation and bit level operation inside the microprocessor. Now before we start learning each instruction one by one, let's first understand what logical instruction actually are. It needs to compare to value, perform logical operation, rotate bit, and manipulate the carry flag. Unlike arithmetic instruction, here we mainly perform addition, subtraction, logical instruction work directly on the binary bit of the data. Most of the operations are performed on the accumulator, which is the primary register used by 8085 microprocessor. Depending on the instruction, different status flags like 0, sign, parity carry and auxiliary carry may also be updated. Let's start with our first instruction, CMP. CMP stands for compare register or memory with accumulator. Now look at the representation in the middle. We can see that accumulator A is compared with either a register or a memory location represented by R or M. One important thing to remember that comparison doesn't mean subtraction is stored. Internally, the processor performs a subtraction only to update the status flag. That means both the accumulator and register remain exactly the same. Only the program status word flags are updated. Now look at these three conditions. If A is small, then the operand, then the carry flag become 1. If A is equal to the operand, then 0 flag becomes 0. If A is greater than the operand, then both carry and 0 flag become 0. So remember, CMP only compares value, it never changes the data. Let's see the example. Here accumulator A is equals to 3AH, register B is equals to 3AH. Since both values are exactly the same, the processor internally compares them. Because they are equal, the 0 flag becomes 1, but the carry remains 0. Notice something important, A is still 3A and B is still 3AH. Nothing changed, only the 0 flag changed. This is exactly why CMP is called as a comparison instruction. Up next we have CPI, compare immediate with accumulator. This working principle is almost identical to CMP. The only difference is instead of comparing with a register, the accumulator is compared with an 8-bit immediate data written inside the instruction itself. Again, look at the diagram. Accumulator on one side and immediate data on the other. And only the flags are updated, neither value changes. Let's see the example. Accumulator contains 75H and the instruction provides 89H. Now compare both values. Since 70H is smaller than 89, the processor sets carry flag to 0 and 0 remains 0 because the values are not equal. Again, A remains 75 and immediate data remains 89, only the carry flag changes. Now let's learn the next instruction, ANA, which stands for logical and register or memory with accumulator. Look carefully at the representation. Accumulator A enters one side of the AND gate and register or memory enters on the other side. The output of the AND gate is stored back to the accumulator. A short trick to remember the AND rule, that 1 and 1 gives 1, everything else gives 0. The single rule is enough to solve any AND operation. Let's solve the example. Accumulator A is equals to C6H and register E contains 3AH. First convert them into binary. C6 means 11000100. 3AH became 00101010. Perform the AND operation at your own. The answer should be 00000010. This binary value is equal 0 to H. So the new value stored in the accumulator became 0 to H. Notice only the accumulator changes, the register value remain unchanged. Also remember after A and A, sign, 0 and parity flag are updated. Carry is reset to 0 and auxiliary carry became 1. Up next we have A and I, which means logical and immediate with accumulator. Everything works exactly like A and A. The only difference is instead of using a register value, we use an 8-bit immediate value. Suppose accumulator contains A7H and immediate data is 86H. Convert both into binary and perform the AND operation. The answer is 86H. Therefore, the accumulator now stores 86H. Again, carry became 0, auxiliary carry became 1. So in this slide, we have learned 4 important logical instructions. CMP compares the accumulator with a register or a memory. CPI compares the accumulator with immediate data. ANA performs a logical AND operation with a register or memory, and ANI performs a logical AND operation with the immediate data. Up next, our next instruction is ORA. ORA stands for logical op between register or memory with accumulator. If you look at the operand column, you will notice that the operand can either be a register or a memory location. The opcode ranges from B0H to B7H depending on which register is used. Now let's understand what actually happens. The processor performs a bit-by-bit OR operation between the content of the accumulator A and the selected register or a memory location. The result is stored back in the accumulator. Notice something important. The original register and the memory remains unchanged. Only the accumulator get updated. After executing ORA, sign flag is updated, 0 flag is updated, parity flag is also updated. The carry flag became 0, auxiliary carry became 0. Let's see the example. Accumulator A contains 56H and register B contains 38H. First, convert both values in the binary and perform the OR operation. Remember the OR rule. If either bit is 1, the answer became 1. So, in this case, the answer gives 01111110. Now convert this binary back into the hexadecimal. This equals 7EH. Therefore, the accumulator now stores 7EH. Up next we have ORI, logical or immediate. The difference from ORA is very simple. Instead of taking the data from a register or memory, it takes a 8-bit immediate data written directly in the instruction. I will not say how the instruction is actually happen, but it is briefly described in the slide. Up next we have XRA. XRA stands for exclusive OR commonly called XOR. This instruction performs a bitwise XOR operation between the accumulator and a register or a memory location. Unlike OR, XOR has a different rule. Remember the simple table I have written at the top of the slide, that 0 XOR 0 gives 0, 0 XOR 1 gives 1, 1 XOR 0 gives 1, 1 XOR 1 gives 0. The simple trick you can remember that when both bits are different, XOR gives 1. Again, sign, 0 and parity are updated. carry became 0 and auxiliary carry became 0. Let's see the example. Suppose accumulator A contains 5AH and register B contains 3CH. Convert them into the binary and perform the XOR operation. Then we obtain 1100 110, converting into hexadecimal 66H. Therefore, after executing XRA B, accumulator became 66H. Up next we have XRI, almost identical to XRA. The only difference, the second operand is an 8-bit immediate value instead of a register or memory value. As this is also exactly same to XRA, I will not explain this. Let's quickly summarize this instruction that ORA performs a bitwise OR using a register or memory. ORI performs a bitwise OR operation using immediate data. XRA performs a bitwise exclusive OR using register or memory. XRI performs a bitwise exclusive OR operation on immediate data. These logical instructions are extremely useful in masking bit, setting bit pattern, clearing bit, or checking condition, and digital data processing. Moving to our next setup operation, these are rotate instruction. Let's start with the first instruction, which is RLC. It stands for rotate accumulator left. Its opcode is 07H. Notice the operand is none. Why? Because RLC always works on the accumulator A. No register or memory location is required. Now look carefully at the visual representation. The accumulator contains 8-bit. Starting from D7, which is the most significant bit, up to D0, the least significant bit, in RLC every bit shifts one position towards left. So here the important part, the bit that leaves from D7 doesn't disappear. Instead, it goes to two places simultaneously. First, it enters the carry flag. Second, it comes back and occupies D0. That's why RLC is called circular left rotation. Think of it like a circle. The leftmost bit leaves from the front and joins again at the back. Only the carry flag changes. The sign 0 parity and auxiliary carry remains completely unaffected. Let's see the example. Initial accumulator contains B2, which is 10110010. Let's perform the left operation. The leftmost bit is 1, comes out of D7. That bit enters to carry flag. At the same time, the same bit is placed back into D0. So after execution, the binary becomes 01100101. Converting into this hexadecimal, we get 65H. Therefore, accumulator became 65H and the carry became 1 because the original D7 was 1. Up next we have RRC. This is actually the opposite instruction of RLC. It stands for accumulator rotate to right. The opcode is 0FH. Again, no operand. Let's observe the diagram. Every bit moves one position to the right. Now what happens to D0? The last bit D0 moves to two places. It enters the carry flag, also come back to D7. So again a circular rotation, but this time towards the right. Example, initially accumulator contains 10110010, which is B2H. Now rotate one position to the right. The last bit D0 is 0. This enters the carry flag and remaining bit shifts right and D0 is placed back into D7. The new binary became 01011001. Converting it into hexadecimal, we obtain 59H. Therefore, accumulator content is 59H and carry became 0. Now comes the most interesting rotate instruction RAL, which stands for rotate accumulator left through carry. Its opcode is 17H. Unlike the previous instruction, it also operates only on the accumulator, but unlike RNC, this instruction also uses the carry flag as a part of the rotation. Look carefully at the diagram. Imagine the carry flag as a 9th bit attached to the accumulator. During rotation, every accumulator bit moves one position to the left. The original D7 moves to the carry flag, but now instead of D7 coming directly back to D0, the old carry flag enters D0. So the carry flag becomes a part of the rotation process. This is why it is called rotate left through carry. Let's see the example step by step. Initially, accumulator contains 10110010, which is B2H. Suppose the old carry flag is 1. Now perform RAL. Every bit shifts left. The original D7, which is 1, moves into the carry flag. Now instead of bringing D7 back to D0, the processor inserts the old carry flag value into D0. Since the old carry was 1, D0 became 1. The remaining bits simply shift left. The new binary becomes 011000101. So accumulator became 65H and the new carry becomes 1 because the original D7 was 1. The important point to remember is this: in RLC, D7 returns directly to D0, but in RAL, the old carry goes to D0 and the D7 moves to the carry flag. This is the main difference between these two instructions. So these rotate instructions are used whenever we need to manipulate bit efficiently. Instead of changing values mathematically, they simply rotate the position of bits inside the accumulator. These instructions are widely used in bit manipulation, serial data transmission, encryption techniques, multiplication and division by the power of 2, and embedded system programming. Our next instruction is RAR, which stands for rotate accumulator right through carry. Notice that its opcode is 1FH and no operand, like all the rotate operations. Look carefully to the diagram. The accumulator contains 8 bits starting from D7 on the left and ending at D0 on the right. Unlike RRC, RAR also uses the carry flag as the part of the rotation. Imagine the carry flag as an extra 9th bit connected to the accumulator. Now see what happens. Every bit shifts one position to the right. The original D0 leaves the accumulator and becomes the new carry flag. At the same time, the old carry flag enters the more significant position, which is D7. So remember this movement: old carry to D7 and old D0 to new carry. This is why this instruction is called rotate right through carry. Only the carry flag changes, the other flags are not affected. Let's understand with the example. Initially, accumulator contains 10110010, which is B2H. The old carry flag is 1. Now execute the RAR instruction. Every bit shifts one position towards the right. The last bit, which is 0, moves into the carry flag. So the new carry becomes 1. Now the old carry, which was 1, enters into D7. The remaining bit simply moves one position right. The new binary becomes 110110001. So the accumulator is updated. The new carry flag becomes 0. This is exactly how RAR works. Let's move to our next instruction, CMA, which stands for Complement Accumulator. Its opcode is 2FH, and again there is no operand. Understand the visual representation. The accumulator contains D7, D6, D5 all the way up to D0. The processor performs one's complement. What does that mean? Every single bit is reversed. Every 0 becomes 1 and every 1 becomes 0. Nothing else changed. No arithmetic, no shifting, only inversion of bits. Also remember, no flags are also affected. Let's see the example. Accumulator contains 10110010, which is B2H. Let's perform the complement. So the answer is 1001101. This binary corresponds to 4DH. Therefore, after executing CMA, the accumulator contains 4DH and no carry flag is affected. Up next, we have CMC, which stands for complement carry. This opcode is 3FH. Again, there is no operand. Unlike CMC doesn't touch the accumulator at all. It works only on the carry flag. The carry flag simply changes to the opposite value. If the carry is 0, it becomes 1. If the carry is 1, it becomes 0. That's all. No other register changes, no accumulator changes, no flag changes. Up next we have STC. It means set carry. Its opcode is 37H. Unlike the previous instruction, it also has no operand. Look at the diagram. The carry flag enters the instruction. Instead of complementing it, the processor simply forces the carry flag to become 1. No matter what the previous value was, after executing XTC, carry became 1. No other register changes, no other flag change. A quick review. RAR rotates all bit 1 position to the right through the carry flag. Old carries enter D7 and old D0 became the new carry. CMA performs a 1 complement to the accumulator. Every 0 becomes 1 and 1 becomes 0. CMC simply toggles the carry flag. 0 became 1 and 1 became 0. STC set the carry flag to 1 regardless of its previous value. One important point to remember is, except changes to the carry flag in RAR, CMC and STC, the 0 sign parity auxiliary carry flags remain unaffected. In today's video, we have completed remaining of the logical operation, rotate and complement instruction of the 8085 microprocessor. In the next lesson, we will move on to the next category of 8085 instruction and continue building our understanding of assembly language programming.
Thank you so much for watching and supporting our content. Your like, comment and encouragement motivate us to create more educational video. If you find this lecture helpful, don't forget to like, share and subscribe to our channel. Happy learning. See you in our next video.